This video covers the Schrodinger equation for matter waves. Erwin Rudolf Joseph Alexander Schrodinger was born on August 12, 1887 and died on January 4, 1961. He was a Nobel Prize-winning Austrian and naturalized Irish physicist who developed fundamental results in quantum theory. Max Born was born on December 11, 1882 and died on January 5, 1970. He was a German-British theoretical physicist who was instrumental in the development of quantum mechanics. He also made contributions to solid-state physics and optics and supervised the work of a number of notable physicists in the 1920s and 1930s. Born was awarded the 1954 Nobel Prize in Physics for his fundamental research in quantum mechanics, especially in the statistical interpretation of Schrodinger's wave function. De Broglie's doctoral thesis, defended at the end of 1924, created a lot of excitement in European physics circles. Following up on de Broglie's ideas, Schrodinger decided to find a proper three-dimensional wave equation for the electron. In 1926, Schrodinger published the wave equation that now bears his name and used it to derive the energy spectrum of hydrogen. There is no simple or easy derivation of Schrodinger's equation, but it can be obtained heuristically by using the connection between light waves and photons, and construct an analogous structure for de Broglie's particles' wave properties. Let us consider a one-dimensional space oscillatory wave temporal function. Let's imagine the argument of this function represents a wave of a certain frequency and wavelength moving from the left to the right. The wave function can then be written as de Broglie's relationships linking the matter-particle momentum and energy with the wave's frequency and wavelength are. Using those relationships, we can rewrite the wave function argument as defining. The wave function becomes the wave function could be a sine or cosine or a complex exponential function or any combination of functions that yield oscillatory behavior. We will impose some characteristics of the wave function and use those characteristics when seeking for a partial differential equation that has this ad hoc wave function as a solution. Let's imagine we would like to solve the differential equation by the method of separation of variables. Then we can split the wave function into two components. According to Max Born, the integral of the square of the wave function over an interval in space is proportional to the probability of finding the particle in that interval at a time t. This is expressed as or the integral of the square of the function over the total spatial domain should not change as the wave function evolves in time so that the proportionality constant does not change. Let's imagine we have one solution valid for a time t of 0, then we have. Therefore, we must have. Which means that the square of the temporal component must be equal to a constant at any time. If this was a real function, then the function should be a constant. But this is not a wave function in time. Let's try a pure imaginary function instead. For an imaginary function we have, and the probability density function is defined as the square of the modulus of the complex wave function. So if the temporal part is expressed as an imaginary function of time, we satisfy the condition that proportionality constant is not a function of time while allowing the function to have an oscillatory behavior. Now let's obtain the differential equation for which this proposed function form is a solution. We want a partial differential equation that is first order in time so that given an initial distribution we can see how the wave evolves in time based on the initial value problem. Let's determine the partial derivative of the wave function with respect to time. Or let's examine now the spatial partial derivative. We need a second-order differential equation so we can have a boundary value problem. Let's assume the function in space is also given by an imaginary exponential form such as so the second partial derivative with respect to x becomes but the particle momentum and energy are related together through the particle's mass as therefore, we have or the temporal first partial derivative and the spatial second partial derivative are let's propose that the differential equation is given by which simplifies to and this is the Schrodinger partial differential equation for a free particle of mass m. The solution of this equation for a free particle is for a particle moving in a non-zero potential field V that is a function only of position, the energy is given by the second derivative in space and the first derivative in time are and Schrodinger equation becomes which can be easily extended to 3 dimensions as this is the time-dependent Schrödinger's equation. The time-independent Schrödinger's equation is the probability density function of the time-dependent equation solution does not change with time and is equal to the probability density function for the time-independent solution. For this reason, the solutions to the time-independent Schrödinger's equation are known as stationary solutions. And there is apparently no need for the solution to be an imaginary function. But some boundary conditions may require the time-independent Schrödinger wave equation to be a complex function. We will proceed now and obtain stationary solutions for a single electron orbiting a nucleus. This is known as the hydrogen atom or hydrogen-like ion solution. We start with the three-dimensional time-independent Schrödinger's equation. We will use spherical coordinates. The spherical coordinate system specifies a given point in three-dimensional space by using a distance and 2 angles as its 3 coordinates. These are the radial distance or along the line connecting the point to a fixed point called the origin, the polar angle θ between this radial line and a given polar axis, and the azimuthal angle phi, which is the angle of rotation of the radial line around the polar axis. The Laplacian in spherical coordinates is then the time-independent Schrödinger equation becomes we will now use the method of separation of variables. Let's imagine the wave function can be written as therefore the partial derivatives are with this, the time-independent Schrödinger equation becomes now we will multiply the equation by we obtain which can be rearranged as and the variables have been separated. So the left and right-hand sides must be equal to a constant. We will use what may seem a weird choice for the constant, but the choice will become clear later. The constant is the product of a number L times L plus 1. At this point, this number can be anything, but as we will see later, L can only take some integer values and is in fact one of the quantum numbers, specifically the azimuthal quantum number. The left-hand side yields the radial time-independent Schrödinger equation. The right-hand side yields the angular time-independent Schrodinger equation. Adrien Marie Legendre was born on September 18, 1752 and died on January 9, 1833. He was a French mathematician who made numerous contributions to mathematics. Well-known and important concepts such as the Legendre polynomials and Legendre transformation are named after him. We will proceed with a second separation of variables for the angular equation. The angular function y can be written as the product of a function θ and a function phi. Then we have we also have. So the equation becomes separating variables we have. We can now equate the left and right-hand side to another constant. This constant is written as the square of a number m sub l. We will soon see that m sub l is the second quantum number or the magnetic quantum number. Let's look for the first equation for function phi. The solution for this equation is of the form. For the function phi to be a periodic function, we must have, which means this condition is satisfied when m sub l is equal to an integer. The constant m sub l that originates from the separation of variables, and is one of the quantum numbers, has its possible values dictated by the periodic condition imposed on the function phi. The allowable values for m sub l are the integral of this function over the angle phi domains must be equal to 1, therefore the solution for function phi is the other equation is. Let's make a transformation of variables. Then we have. Using this, the equation becomes, which simplifies to. That can be written as. This equation is known as the general Legendre differential equation. The solution is expressed in terms of associated Legendre polynomials of degree L and order m sub L. The ordinary Legendre polynomials are the polynomial solutions of the Legendre equation when m sub L is 0, and they can be constructed using Rodriguez formula. The associated Legendre polynomials can be expressed in terms of derivatives of the ordinary Legendre polynomials of degree L as the term -1 raised to the m sub L power is known as the Condon-Shortley phase. Therefore, we have, due to the order of the derivative terms, the values of m sub L must be in the range of -L to L. And this is a restriction on the allowable quantum numbers of the orbitals. A closed form for the associated Legendre polynomials is for the integral of the square of the function to be equal to 1 over the angular domain, we need to have a normalizing factor. Finally, the combination of the angular components of the stationary Schrödinger's equation is the functions y are known as the spherical harmonics. The first few spherical harmonics are You may recognize the nomenclature used for the constants during the separation of variables as the indexes taught in chemistry classes for the atomic orbitals. We will see this in more details later, but for now it is important to highlight that the orbital indexes, L and m sub L, arise from the solution for the spherical harmonic functions of the time-independent angular components of Schrödinger's equation. There are many graphical representations of those orbitals in the literature. We will show some. In this picture, the complex spherical harmonics are represented on polar plots. The magnitude of the spherical harmonic at particular polar and azimuthal angles is represented by the saturation of the color at that point, and the Condon-Shortley phase is represented by the hue at that point. In this picture, the complex spherical harmonics are represented on polar plots. The magnitude of the spherical harmonic at particular polar and azimuthal angles is represented by the radius of the plot at that point, and the Condon-Shortley phase is represented by the hue at that point. In this picture, the real spherical harmonics are represented on polar plots. The amplitude of the spherical harmonic, magnitude and sign, at a particular polar and azimuthal angle is represented by the elevation of the plot at that point above or below the surface of a uniform sphere. The magnitude is also represented by the saturation of the color at a given point. The Condon-Shortley phase is represented by the hue at a given point. According to Bohr's atomic model, an orbit refers to a circular path around a nucleus where an electron is said to revolve. Bohr model's orbits are located a certain radial distance from the nucleus depending on the electron energy. In Bohr's model, there is no explanation for why an electron orbiting a nucleus, and therefore continuously being accelerated, does not lose energy eventually collapsing onto the nucleus. Even the assumption that the energy levels were quantized did not provide a clear explanation for why orbiting electrons do not emit radiation. In quantum physics, an orbital represents a three-dimensional region around the nucleus where an electron is most likely to be found. Another interesting representation of orbitals is the orbital dot plot. The dot plot is a presentation of electron density within an atomic orbital, where dots are used to depict the probability of finding an electron at a particular location in space, with denser clusters of dots indicating areas of higher electron density within the orbital. Essentially, it's a way to visualize the shape and distribution of an orbital probability density function. In the quantum physics approach, an electron is not orbiting or traveling along an orbit. Quantum physicists says instead that the electron occupy an orbital. This interpretation results in no movement required by the electron, and therefore the electron is not accelerating and does not emit radiation. The electron can change the orbital it occupies if it gains or loses energy by some process, but this does not require the electron to move. It just simply stops occupying an orbital and occupies another one with the appropriate energy level. Illustrations of the electron moving or circling orbitals is incorrect according to the correct quantum physics interpretation of what an orbital represents. The angular component of Schrödinger's equation describes the angular probability density function of the electron in an orbital. It is a different approach than the one described in Bohr's model, where the orbits were seen as fixed circles around the nucleus. Edmond Nicolas Laguerre was born on April 9, 1834 and died on August 14, 1886. He was a French mathematician. His main works were in the areas of geometry and complex analysis. He also investigated orthogonal polynomials that now bear his name, Laguerre polynomials. He laid the foundations of a geometry of oriented spheres. The time-independent radial Schrödinger equation is: for an electron orbiting a hydrogen-like ion, the potential V is. Therefore, the equation we are seeking to solve is we will start with the following function transformation. Then we have so the radial equation becomes which is simplified to defining. We have Substituting this into the radial equation yields the Bohr radius is defined as, so the radial equation can be written as let's define. With this we obtain Bohr energy levels were defined as, and the Bohr radius is. Combining those equations, eliminating the electric charge yields. Using this, the radial equation becomes, we want the behavior of the radial function to be 0 as r or s tends to infinite. This condition yields the solutions are, the only solution that works as s tends to infinite is when r or s tends to 0, the equation can be approximated as we conduct now a transformation of variables. The equation becomes the solution is the only solution that works as s tends to 0 is let's try a power series expansion in terms of a polynomial L of s and multiply the polynomial by the two limiting functions as s tends to 0 and infinite. The proposed solution is then the first and second derivatives are the equation we are trying to solve is, and substituting the equations for the proposed solution and its second derivative we obtain, which simplifies to, this is the generalized Laguerre equation. The closed form solution for the generalized Laguerre polynomials is, or, let's compare the radial equation for L of s and Laguerre differential equation for y of x. We conclude that. Let's now modify the notation from the Laguerre polynomials of order m and alpha to polynomials t of orders n and l, which are the separation of variables constants in the radial equation. The polynomials t can be written as for this polynomial not to diverge, we must have let's obtain the first three polynomials t for L value of 0 and n values of 1, 2 and 3. We will see later that this corresponds to the 1s, 2s and 3s orbitals. Those polynomials are we can now rewrite the function chi as we will now transform the function chi back into the function r, but keep the independent variable as s for the moment. Using the definitions, we obtain, and we can write the function r as the wave equation is, then the normalization factor a can be determined from, but the spherical harmonics are already normalized, so what is left is only the radial component. The normalization factor can then be determined from but we have using the relationship between r and s. We can write the normalization condition is then substituting the expression previously obtained, we get it can be shown that so finally, the normalization factor is and we can write the radial equation as using the relationship. We obtain the solution for the time-independent radial component of Schrödinger's equation for a hydrogen-like ion. Let's determine the radial solution for an L value of 0 and N values of 1, 2, and 3. Those are the radial solutions for orbitals 1s, 2s, and 3s. There are some interesting results that can be obtained from the radial solution for L of 0. Nodes are points in space where the probability density function is 0. We can see that the radial probability density function for n of 1 has no nodes. However, the solutions for n of 2 and 3 have nodes. For n of 2 we have only one node given by For n of 3 we have two nodes. The nodes for n of 3 are. This picture illustrates the orbitals 1s with no nodes and 2s and 3s with their respective nodes. Finally, Schrödinger's time-independent equations for the hydrogen-like ions are This solution involves several quantum numbers. The principal quantum number is denoted n. It tells the average distance of an electron from the nucleus. As n increases, so does the average distance of an electron from the nucleus. All wave functions that have the same value of n are said to constitute a principal electron shell. The principal quantum number n corresponds to the number n used by Bohr to describe electron orbits and by Rydberg in his empirical formula for the hydrogen spectrum. The possible values for n are the electron energy is quantized as, where r is the Rydberg constant. This result is consistent with Rydberg empirical formula for the hydrogen spectrum and the energy levels proposed by Bohr. The azimuthal quantum number, denoted L, is the second quantum number. The value of L describes the shape of the region of space occupied by the electron. The allowed values of L depend on the value of n and can range from all wave functions that have the same values of both n and L form an electron subshell. The regions of space occupied by electrons in the same subshell usually have the same shape, but they are oriented differently in space. Chemists use the labels S, P, D, and F to refer to the azimuthal quantum numbers. This nomenclature is based on the spectral lines for alkali metals that were classified as sharp, principal, diffuse, and fundamental, or fine series, based on their visual appearance. The magnetic quantum number denoted as m sub L describes the orientation of the region of space occupied by an electron with respect to an applied magnetic field. The allowed values range from each wave function with an allowed combination of n, l, and ml values describes an atomic orbital. Otto Stern was born on February 17, 1888 and died on August 17, 1969. He was a German-American physicist and Nobel laureate in physics. He was the second most nominated physicist for a Nobel Prize, with 82 nominations in the years 1925 to 1945. Walter Gerlach was born on August 1, 1889 and died on August 10, 1979. He was a German physicist. In 1921, Otto Stern conceived an experiment that was successfully conducted first by Gerlach in early 1922. In the experiment, a beam of atoms is sent through a spatially inhomogeneous magnetic field with a definite field gradient toward one of the poles. It is observed that the beam splits into two beams as it passes through the field region. This indicated that electrons in the atoms have a degree of freedom capable of coupling to the magnetic field. That is, an electron has an intrinsic magnetic moment. The implication of the Stern-Gerlach experiment is that we need to include a fourth quantum number, the electron spin m sub s, that can only take two possible values. Wolfgang Ernst Pauli was born on April 25, 1900 and died on December 15, 1958. He was an Austrian theoretical physicist and a pioneer of quantum physics. In 1945, after having been nominated by Albert Einstein, Pauli received the Nobel Prize in Physics for his decisive contribution through his discovery of a new law of nature, the exclusion principle or Pauli principle. In the case of electrons in atoms, the Pauli exclusion principle can be stated as follows. In a Pauli electron atom, it is impossible for any two electrons to have the same values of all four of their quantum numbers, which are n, the principal quantum number, l, the azimuthal quantum number, m sub L, the magnetic quantum number, and m sub s, the spin quantum number. For a given set of quantum numbers, each principal shell has a fixed number of subshells, and each subshell has a fixed number of orbitals, and each orbital can be occupied by a maximum of two electrons with opposite spins. The atom charge distribution is central to chemistry because it is related to chemical reactivity. As an example, let's see the s orbital's radial wave function solutions. We can see that for a given orbital, there may exist a radial position where the wave function is zero, and as a consequence the probability of finding the electron at that location is zero. Those locations are called nodes. The 1s orbital has no nodes, the 2s orbital has one node, and the 3s orbital has two nodes. The energy levels for a single electron orbitals depend only on the first quantum number n. The expression is exactly the same obtained using Bohr's model. So all subshells and orbitals of a shell have exactly the same energy level. However, for multi-electron atoms and ions, the orbitals interfere with each other, distorting their shapes, and the energy levels vary following a pattern shown in this table. To determine the electron configuration for any atom, we can build the structures in the order of increasing atomic numbers, beginning with hydrogen, and continuing across the periods of the periodic table. We add one proton at a time to the nucleus and one electron to the proper subshell until we have described the electron configurations of all the elements. The periodic table arranges the elements according to their electron configuration. The Schrodinger atomic model describes electrons as wave-like particles that occupy regions of space called orbitals, where the probability of finding an electron is highest, rather than following fixed orbits around the nucleus. Unlike previous models, it essentially depicts the electron as a cloud surrounding the nucleus due to its probabilistic nature.